All right, welcome back. Now we are going to get into the good stuff, which is actually using what we have just talked about to graph. So now that you know how to find your vertical and horizontal asymptotes and your removable discontinuities, let's graph. So again, here are our steps. We'll plot our vertical and horizontal asymptotes with dotted lines. We'll use a table to find key points so that we can get a clear picture of the shape of our graph. Remember, your removable discontinuities are holes, so we're going to graph those with an open circle. And so let's jump into example 3 here. So the first thing I'm going to do is factor my function. In that numerator, I have a difference of squares. And in that denominator, that is going to be x plus 3 times x minus 1. So I know about that my domain exclusions are going to be that x cannot equal 1 or negative 3. So I have to do some further work to determine if these are going to be a hole or a vertical asymptote or neither. So looking here, these do have a common factor, so this will simplify to x plus 1 over x plus 3. So that means the discontinuity that was removed is the x equals 1, so that's going to be the the x coordinate for my hole. So to find that y coordinate, I'm going to plug 1 into my simplified function. So 1 plus 1 over 1 plus 3 is 2 over 4, which equals 1/2. So that's the coordinate for my removable discontinuity, which means my vertical asymptote is my leftover domain exclusion. Now for my horizontal asymptote, I need to look at the degree of my exponents. Now, I can do this for my original or my simplified. Either way, it will be the same. Notice here, these both have a degree of 2. These both have a degree of 1. So either way, it's going to be eats DC, which means you divide your leading coefficients, and in each case, all are 1. So your horizontal asymptote is going to be at y equals 1. So what I'm going to go ahead and do is get all of these on my graph below here. My dashed line here at my vertical asymptote, my dashed line here at my horizontal asymptote, and then an open circle at 1 and 0.5. I'm just going to kind of eyeball that. So there are going to be 2 parts of my graph on either sides of these intersecting asymptotes. So I need to figure out if that's going to be up here, or down here. So that is where my table comes in. So what I'm going to do is plug in some values to the left of this vertical asymptote. So I'm going to go -5 and -4 to see where that gets me. So in my y equals, I'm going to put in my simplified function, x plus 1 over x plus 3. And then in my table, I'm going to do -5 and -4. And I get 2 points here. So -5, 2, -4, 3. And if I went a little further, like -3.5, you can see that it's going to be increasing. 3.5 would be up here at 5. If I went to like -6, notice it's getting smaller, closer to 1, but not quite touching. So that tells me that my graph is going to curve this way along my 2 asymptotes. Okay, so then to get the second part of my graph, I'm going to look for x values that are on the other side of my asymptote. So like -2, -1, 0. And then I know it's going to end up touching that hole there. And look, I've got -1, 0, 1/3. So -2, -1, -1, 0, 0, 1/3. So my graph down here is going to hug those asymptotes this way. So that's what your table helps you do. It helps you figure out where around your asymptotes the graph exists. Let's do one more example. Here's example 4. I cannot factor the top. So if I'm looking at the bottom, I do have a difference of squares. So that is going to be x minus 2 times x plus 2. So my domain exclusions are going to be that x cannot be +2 or -2. And I do not have anything to simplify, so I'm not going to have a removable discontinuity. Instead, I'm going to have two vertical asymptotes at x equals 2 and x equals -2. Now moving on to my horizontal asymptote, my degree in the top is 1, my degree in the bottom is 2. It's bigger on bottom, so BOBO, that means that my horizontal asymptote is going to be at y equals 0. So I'm going to go ahead and get those asymptotes on my graph. I have a vertical asymptote here. So there is my first dashed line. I have another asymptote here. And then my next one, y equals 0, that's the y-axis. So I'm going to put it just a little bit above so that we can see it. Now, because I have two vertical asymptotes, I'm going to have 3 parts to my graph. So I'm going to need to make sure I get x values that are to the left of this asymptote, x values that are in between these two, and x values that are to the right. So let's start with a few. Let's go with what's on the left first. So I'm going to go with -4 and -3 just for funsies. Let me swap out the function that's in here. I need to have x minus 1 divided by x squared minus 4. And then in my table, I'm going to do -4, -3. So this is like -0.41, -0.8. If I went further, let's say like 2.5. Notice that it's getting larger, but in the negative direction. So that tells me that my graph is going to be hugging my asymptotes this way. Okay, now I'm going to go ahead and do the ones on the right side. So I'm going to start with like 3, 4, and 5 just to see what our graph is doing there. And I'll save the middle for last. So I've got 0.4, 0.25, 0.19. So they're getting closer and closer to 0. So if I were to do a number between 2 and 3, like say 2.5, 2.4, notice that it's getting bigger. So it's going to hug my graph this way. So that leaves the middle. I'm just going to add another row down here for x and y's. And I should only need a few. So let's go with like -1, 0, and +1. So I've got 2/3, 0.25, and 0. So that's going to look kind of like this. And if I went further to like 1.5, notice that it's going to dip down into the negative. So this part of the graph is going to look like this. Kind of like a cubic in the middle, sort of shape. So if you wanted to make sure that you had this done correctly, you could hit that graph button, of course, but you will need to know how to do these by hand as well. And that concludes part 2 of graphing your rational functions. We'll be doing more with this again next class, but looking at it from the lens of transforming your parent function.